Okay, so you know how for like 70 years people have been talking about this dream of like clean and basically endless energy from nuclear fusion?
Yeah,
Like it's always felt like this just amazing future that's almost here but not quite. And
right.
what if I told you that with the help of some really, really smart AI, that future is like closer than it's ever been?
Absolutely. And, that's exactly what we're going to be diving into today on this deep dive.
Mhm.
We're going to be looking at nuclear fusion and some really significant progress that's been made recently.
Right.
We saw the U.S. Department of Energy hit this like landmark achievement of net energy gain. And now there's this truly fascinating development coming right out of Germany.
And that's what we're going to be focusing on today. We're
Yeah.
going to be zooming right in on the German facility, the Wendelstein 7X Stellarator.
Yes.
And we're going to explore the truly mind-bending role that artificial intelligence is playing in all of this,
Yeah.
in pushing fusion from like a dream into an actual reality.
Yeah.
And our goal today, for you listening, is to really understand these major milestones, get a good grasp on the different ways scientists are actually approaching fusion, and just see how AI is like this secret weapon that's speeding up the process to a clean energy future
Exactly.
for everybody.
Yeah.
Okay, so
Yeah.
let's unpack this a little bit. What exactly is this like holy grail of fusion that we keep hearing about?
Well, at its most basic level, nuclear fusion is the process of taking atomic nuclei and joining them together. And we're usually talking about isotopes of hydrogen here.
Okay,
So think of those as like slightly different versions of a hydrogen atom.
got it.
And you're smashing them together to create a heavier nucleus, like helium, for example. And when this happens, a tremendous amount of energy is released.
Yeah,
And this is the same process that's happening right now in our sun.
right.
What makes this so appealing is that unlike nuclear fission, which involves splitting atoms and creates that long-lived hazardous radioactive waste,
Right.
the main byproduct of fusion is helium, which is inert and totally harmless.
Mm.
So you can really start to see the potential there for a safe and clean energy source.
Absolutely. And I think that contrast with fission
Mhm.
is so important to highlight
Right.
because it really does solve that issue of what do we do with this dangerous waste and how do we store it long term?
Exactly.
Now, you mentioned ITER in France,
Mm.
and that's like another major player in the fusion world, isn't
Yeah,
it?
it's this massive collaborative project, and they're really focused on proving that this tokamak concept can work.
Okay.
So a tokamak, you can think of it like this giant magnetic bottle.
Okay, right.
It's shaped like a donut or technically a torus.
Right.
And you use these powerful magnetic fields to contain this incredibly hot plasma. And plasma is just that state where the electrons are stripped away from the atoms.
Got it.
You contain that within this donut-shaped chamber. And the scale of ITER is really, really impressive. They have 24 superconducting magnets. So these are special magnets that when you cool them down to extremely low temperature, they can conduct electricity with virtually no resistance. So you can get these super strong magnetic fields. And some of these magnets weigh up to 400 tons.
Wow.
They're designed to create those incredibly strong magnetic fields that you need for this whole thing to work.
400 tons, that really gives you like a sense of the scale
Yeah,
and the power involved here.
sure.
But I remember reading that there's this big challenge with the tokamak approach.
Right.
It's something about not being able to run continuously. Is that right?
Yes, that's a really critical limitation, actually. So current tokamak designs, including ITER,
Yeah.
they're fundamentally limited to what we call pulsed operation. So the fusion reaction tends to extinguish itself after just a few hours, and then you have to restart it, which is costly and energy intensive.
Yeah.
You can think of it like an oven that just keeps turning itself off every few hours, which isn't very practical if you want like a continuous supply of power.
Right.
So while ITER is really important for pushing our fundamental understanding of fusion forward,
Yeah.
and demonstrating that the core technology works this on-again, off-again nature of it presents a real challenge if we want to turn it into a practical, always-on power plant.
For everybody to actually use.
Exactly.
Right. That on and off issue with tokamaks really does sound like a major hurdle
Oh, yeah.
if you want to use it for power generation.
Yeah,
And it really makes you wonder if there's a different way to keep that fusion fire burning continuously.
right.
So that brings us to Germany and the Wendelstein 7X. This is a completely different type of machine.
Yeah, it is.
They call it an optimized stellarator.
Right.
So what is the idea behind that?
So the Max Planck Institute in Germany has been taking a different approach with the Wendelstein 7X. Now, the Stellarator concept itself isn't new. In
Okay.
fact, it actually predates the tokamak.
Interesting.
But for a long time, it was considered less promising.
Yeah.
However, advances in supercomputer simulations have really changed things.
Yeah.
These simulations have allowed scientists to design much more sophisticated and effective stellarator geometries.
So instead of that kind of simple donut shape of the tokamak,
Hmm.
what are we looking at with this stellarator?
Imagine you take that donut shape of a tokamak and then you twist it multiple times, like you're wringing out a wet towel.
Okay.
That complex shape that you get, that's the heart of the stellarator design.
Got it.
And it's not a perfect torus. It's more like this intricate, multiplied, twisted band
Okay.
that forms the plasma confinement area in the Wendelstein 7X. And this unique and carefully calculated shape, which they achieved through these elaborate supercomputer simulations, is absolutely essential to how it performs.
And what does that specific shape achieve?
Right.
Why is it so important?
What's really fascinating here is that this precisely calculated shape ensures that every single particle within that superheated plasma
Yeah.
experiences the exact same magnetic field as it travels along that really complex, twisted path. And this uniformity in the magnetic field is essential for the stability of the plasma and for keeping it contained for much longer periods, without the disruptions and instabilities that you often see in tokamaks.
Interesting.
Each of the incredibly powerful magnets that create this complex magnetic field weighs 6 tons.
Wow.
And their precise arrangement down to the millimeter is absolutely crucial for keeping that incredibly hot plasma on its path and away from the reactor walls.
Right.
Because if that 100 million degree plasma touches the walls even for a moment, it'll cool down instantly and the fusion reaction stops.
6 tons per magnet.
Yeah.
And they're arranged with that level of precision.
Yeah.
And I can only imagine the kind of heat those inner walls have to withstand.
Right.
We're talking about temperatures far hotter than what a spacecraft experiences during re-entry.
Exactly.
So if you're listening, just think about the most intense heat you can imagine
Right.
and then multiply that many, many times.
Exactly. The inner walls have to be built to withstand temperatures many, many times greater than that. And inside the plasma reaches an astounding 100 million degrees Celsius. And it's at these extreme temperatures that the hydrogen nuclei can overcome their natural repulsion and fuse together to form helium,
Right.
releasing that huge burst of energy. And that's the same energy source as the sun's core. And to manage all this heat, they've installed a very sophisticated cooling system,
Okay.
which is basically 7 kilometers of water pipes snaking through the reactor.
7 kilometers.
Yeah.
That's an amazing feat of engineering.
Yeah.
Now, with anything involving this much power, safety is always a big concern.
Right.
So what kind of safety measures are in place with this Stellarator design?
So that's a really important question. And unlike traditional nuclear fission reactors,
Yeah.
a runaway chain reaction or a meltdown is just physically impossible in a fusion device like this.
Okay.
The amount of fuel present in the plasma at any given time is tiny. We're talking about a single milligram of hydrogen.
Okay.
And if there's even a small disruption in the magnetic field or in the plasma itself, it'll immediately cause the fusion process to stop entirely. It's inherently self-limiting and very safe in principle.
That's good to hear.
Yeah.
So what was the big milestone that the Wendelstein's 7X achieved recently that has everybody so excited?
The big achievement was that they managed to generate and contain this high-temperature plasma with an energy expenditure of 1.3 gigajoules, and they sustained it stably for over 8 minutes.
Wow.
Now, this particular experiment wasn't focused on net energy gain like the U.S. experiment was,
Okay.
but it showed something really important. It showed that stellarators can provide this long-duration stable plasma confinement.
Right.
And that's a big step forward in proving that stellarators could be a viable pathway towards continuous fusion power.
Okay, so 8 minutes of sustained plasma.
Yeah.
At those temperatures, that's incredible.
It's pretty amazing.
It really does sound like the Stellarator approach, which was once considered less promising,
Right.
is now showing its true potential. And you mentioned artificial intelligence playing a big part in this.
Yeah.
How exactly is AI helping with these breakthroughs?
This is where things get really interesting. So AI is proving to be incredibly useful in speeding up scientific discovery in all sorts of fields, and fusion research is no exception.
Okay.
One of the big things AI can do is run vast numbers of complex simulations extremely quickly. And for something as mind-bogglingly complex as the behavior of plasma,
Right.
within these magnetic fields,
Yeah.
AI algorithms can explore millions of potential configurations and fine-tune tons of parameters in a fraction of the time it would take humans to even think of them.
So it's almost like having this like super smart, super fast lab assistant
Yeah.
that's
Yeah.
testing out tons of ideas at the same time.
Exactly, and it's more than just simulations.
Okay.
Google's DeepMind has created AI systems that can actually control the plasma infusion experiments themselves.
Wow.
Think about all the tiny adjustments that need to be made constantly to these magnetic fields
Yeah.
to keep that plasma stable. It's a crazy complex system.
Yeah.
DeepMind's AI has shown it can learn in real time how to control those magnets to create and maintain the plasma shapes they want, both in simulations
Yeah.
and in real tokamak experiments.
So the AI is not just looking at the data after the fact, it's actively controlling the experiment itself.
Exactly.
Yeah.
And fusion is a particularly big challenge for AI
Okay.
because it's this continuous and what researchers call underobserved system.
Got it.
Unlike something like a game of chess where you have these clearly defined turns,
Yeah.
the plasma is always evolving, and we can't measure all the important aspects of it all the time with perfect accuracy.
Right.
But even with all this complexity and the limited data, AI is making huge strides
Yeah.
in understanding and controlling this crazy hot ionized gas. And it's definitely speeding up the process of developing fusion reactors that we can actually use.
It really feels like we're on the verge of something big in terms of how we get our energy.
Yeah.
And it's not just one country doing all of this, is it?
No, it's a global effort.
You mentioned China's efforts earlier, right? China is investing a lot in this field, and they've achieved some really impressive things with their own reactors.
Okay.
They're aiming to achieve fusion reactions that last for weeks, not just minutes.
Wow.
And that shows you how seriously the world is taking this. Everyone recognizes the potential of fusion to solve our energy problems in the long run. And it creates a healthy competition which could actually benefit all of us in the end by pushing things forward faster.
So let's sum up what we've talked about today. We've seen some really big steps taken towards achieving nuclear fusion. The U.S. reached net energy gain.
Right.
And in Germany, the Wendelstein 7X showed that they could create stable plasma for a long time. We also talked about the differences in design between the tokamak with its donut shape and the Stellarator with its more complex, twisted geometry. And we've seen how AI is not just some futuristic idea, but it's an essential tool that's helping us overcome some of the biggest challenges in this field.
Yeah. Those recent milestones are really significant. They show that we're finally making some real progress in dealing with the scientific and engineering hurdles of getting sustained and possibly even continuous nuclear fusion.
Yeah.
The tokamak and the Stellarator both have their pros and cons, and AI is becoming more and more important in helping us develop both of these designs.
Right.
The dream of clean and plentiful energy from fusion is starting to look more and more achievable.
Absolutely. This is such an exciting time to be following this field.
Yeah.
It really makes you think, considering how fast AI is advancing and this global race to harness the power of fusion,
Right.
what could the world's energy situation actually look like in the next couple of decades?
Right.
What new breakthroughs might we see that could completely change the game
Yeah.
and affect the way we power our lives?
Right.
It's definitely something to think about.
For sure.
Some pretty profound stuff.
Absolutely.
Well, that's all the time we have for today. Thanks for tuning in to this deep dive on nuclear fusion and AI, and we'll see you next time.
Sounds